Welcome to the Explainer. So today we're actually digging into the hidden, honestly almost ancient mathematics that laid the exact foundation for modern artificial intelligence and language models. Way before we had these massive neural networks just spitting out essays in seconds, text generation relied on a surprisingly elegant system of basically counting. We're going to completely demystify the evolution of text generation today, looking specifically at the huge jump from n-grams to transformers.
Okay, let's dive into this. Here's our mental map for today's explainer. We'll start with the era before the Transformers, tackle the infamous zero-count catastrophe, explore the art of smoothing, look at measuring AI confusion, and finally wrap up with why n-grams still matter today. It's a clear step-by-step journey, so let's get to it.
All right, kicking things off with part one, before the Transformers, the era of counting.
Let's rewind the clock to the 1980s. Deep learning, at least as we know it today, just didn't exist yet, and language modeling relied completely on simple, brilliant math. But to really grasp this era, we've got to establish our baseline terminology. So what exactly is an n-gram? Well, simply put, it's a sequence of n consecutive tokens, which usually means words. A unigram is one word, a bigram is two words, a trigram is three consecutive words. You get the idea. This super simple sequence was the foundational unit of measurement for predicting exactly what word comes next in a sentence.
The actual process of training an n-gram model, it is highly mechanical and, honestly, beautifully logical. You didn't need some massive supercomputer. You literally just needed to count. Step one, you just count how often a specific word follows previous words. Say you're scanning your text and you notice that right after the phrase the cat, the word sat appears exactly 47 times. Maybe the word jumped shows up 12 times and, refrigerator appears 0 times. Step 2, you normalize those counts, so you get a probability distribution. In step 3, you just use those probabilities to predict the next word. It's elegantly simple, right?
The truly wild thing is that before recurrent neural networks or word embeddings even hit the scene, this basic counting mechanism literally ruled the world. From about 1980 all the way through 2015, n-grams ran every single speech recognizer, every spell checker, and every phrase-based machine translation system out there. It was the absolute industry standard. But, as we're going to see in just a second, this whole counting method had a pretty massive fatal flaw.
Which brings us to section 2, the zero-count catastrophe, or when AI basically blanked. All right, here is the mathematical villain of our story, the thing that completely broke those early language models. Think about this for a second. What happens when the model sees a brand new sequence of words it has never encountered before? We just established that the model relies 100% on counting past occurrences. So if a sequence wasn't in its training data, its count is exactly 0.
Now check out this staggering number, 30%. There was this 2007 study looking at the Brown corpus, and it found that even in a 4-gram model, so looking at sequences of just 4 words, a massive 30% of the 4-grams in the held-out test data were completely unseen in training. That means almost 1/3 of the sequences the model was being tested on had a count of exactly 0. 0!
So why does this matter? Well, a raw count-based model assigns 0 probability to anything it hasn't seen. And this is catastrophic. Sentences are long, and almost every long sentence is going to contain at least one unseen sequence. If you remember your probability math, multiplying anything by 0 just wipes out the entire equation. If even one single n-gram in a sentence has a 0 probability, the model looks at the whole sentence and says it's mathematically impossible. You just cannot evaluate real text without fixing this zero count problem. And that leads us right into section 3, the art of smoothing, a true testament to human ingenuity.
So how exactly did engineers save their models from just flatlining? Through about 50 years of really dedicated research that culminated in something called smoothing. Let's define that real quick. Smoothing is basically the process of reallocating probability mass so unseen events get a non-zero probability. It's this clever trick of shifting a tiny bit of probability away from the sequences we have seen and handing it over to the sequences we haven't seen, strictly to avoid those mathematical zeros.
Now, this definitely wasn't an overnight fix. It was more like an evolutionary staircase. Engineers started with pretty blunt instruments, like Laplace or add-1 smoothing, literally just adding a 1 to every single count. But when that failed on rare words, they tried shifting mass based on frequencies, dropping down to shorter word sequences with backoff and absolute discounting, just constantly iterating. Finally, after decades of trial and error, they hit the absolute pinnacle of this research, Kneser-Ney smooth.
Now, what's really interesting here is the stark contrast between the standard approach and the Kneser-Ney breakthrough. On the left side, naive absolute discounting uses raw frequency. It's just looking at how often a word appears overall, end of story. But on the right, Kneser-Ney introduces this truly deep insight. It uses continuation probability. Instead of just asking, hey, how often does this word show up? It asks, how many different contexts does this word actually appear in?
Let's break this down with a highly intuitive example. Think of the city San Francisco. It's a very common bigram, right? Now, if we look at the unigram Francisco all on its own, it has a super high raw count in the text just because the city is mentioned a lot. A naive model would give Francisco a high probability of appearing after any random word just because its raw count is huge. But Kneser-Ney, it notices that Francisco appears in almost exactly one rigid context, right after the word San. So it correctly assigns Francisco a super low continuation probability for other contexts. It perfectly proves why raw counts can be incredibly misleading.
All right, moving on to Section 4, measuring AI confusion and the Perplexity metric.
With all these genius smoothing techniques in place, researchers obviously needed a way to mathematically prove their models were actually getting better. And I really want you to remember this golden rule. If a word is surprising, the model is bad. That is the fundamental philosophy of evaluating a language model. The entire goal is to accurately predict what comes next. If the actual next word surprises the model, well, it means the model doesn't truly understand the language patterns. Perplexity is simply the mathematical tool we use to turn that feeling of surprise into a hard number.
Here is the formal textbook definition for you. Perplexity is the exponent of the average negative log likelihood per word on a held-out test set. And, crucially, lower is always better. But let's completely de-jargonize that for a second. You can really just think of perplexity as the model's official score for confusion. The lower the confusion score, the better the model is at predicting the text.
This concrete analogy is extremely helpful to visualize what's going on. A perplexity score of 100 basically means the model is exactly as confused as it would be if it had to choose uniformly among 100 different words. Literally, imagine staring at 100 words thrown in a hat and having to blindly guess the right one. That is a perplexity of 100. So naturally, you want that number to shrink as close to 1 as humanly possible.
And this sheer performance gap right here explains exactly why the entire AI industry underwent a massive paradigm shift. Just look at these numbers. On the Brown corpus test set, a well-tuned Kneser-Ney 4-gram model, which again was the absolute peak of counting-based AI, hits a perplexity of around 140. But a modern transformer language model on the exact same test set, it hits a perplexity of 15 to 30. That is roughly a 10x improvement. The transformer is literally 10 times less confused. That sheer massive gap is exactly why the field entirely moved on to deep learning. Which brings us to our final section. Section 5. Why n-grams still matter. The enduring legacy. Here is the final narrative twist of our explainer. Despite getting completely crushed by transformers in perplexity scores, these older counting algorithms are far from dead. N-grams have a surprisingly robust modern legacy. First off, they remain the absolute gold standard for classical NLP teaching. They offer the clearest exposure to probability concepts and smoothing. Second, production n-gram libraries like KNLM are still actively used today. They act as rescores in speech and translation systems where you need ultra-low latency. Third, they actually run the on-device autocomplete on your phone's keyboard right now, purely because they are so cheap to run locally. And finally, they serve as absolutely essential neural language model baselines. So the crucial point is this. If you are out there building a modern neural language model and your massive, incredibly expensive transformer doesn't beat a simple Kneser-Ney n-gram baseline by a wide margin, something is fundamentally wrong with your neural network. Calculating this baseline remains the ultimate mathematical sanity check for deep learning engineers today. Modern deep learning directly inherited its empirical tradition from the 50 years of smoothing research that went into perfecting n-grams.
Which leaves us with this final thought. Next time you're typing out a text message and your phone smoothly predicts the next word with zero lag and zero battery drain, ask yourself, have you appreciated the trigram model running perfectly locally on your device's keyboard today? The quote-unquote ancient math of counting words is still quietly powering our everyday tech. Thank you so much for joining me on this explainer, and keep exploring the incredible architecture behind the technology we use every single day.